So, welcome to the next lecture on signals and systems, in which we embark on a new subject. So far, we have been talking about the systems and their behavior purely in the domain in which the signals are constructed. For example, if the signals are on time, we have been talking about the time domain behavior of the system. If the signals are on space, naturally it means we talk about the space domain behavior, all right? So, we do not change the domain, or we do not look for alternative domains in which to either represent the signal or to analyze the system and its behavior. Today, we start our journey towards that objective, right? In other words, we first look at the following issue that we have implicitly raised so far. You see, what was the basic idea behind analyzing linear shift invariant systems the way we did? The idea was that we identified a set of objects, mathematical objects, or in the case of discrete time systems, we identified a specific class of sequences whose outputs were representative, the outputs to which from the system were representative of the system behavior. So, for a linear shift invariant system, we saw that if we chose the unit impulse in time, for the both for the continuous and for the discrete time case, then the output of the system to the unit impulse was representative of the system behavior in its entirety. Another way of looking at this principle was to say that if you looked at any arbitrary input, then the input could be thought of as a linear combination of the unit impulse and its translates, or a set of basis objects constructed out of the unit impulse. The same went through for discrete time systems, where we took the sequence and its translates, all right. So, the question now arises to our minds when we put the whole discussion in this perspective, that there could be other such basis functions, right. So, I mean, is the unit impulse or is the unit impulse sequence the only kind of basis function that we need to deal with, or are there other such basis functions that can also enable us to express an arbitrary input and therefore analyze the behavior of the linear shift invariant system, right? A little bit of historical background, right? I mean, it's interesting how important this question of using basis functions has been, not necessarily only in electrical engineering. In fact, it started even with the analysis of vibrating strings, or in the analysis of heat flow mechanisms, which has been, an endeavor in physics and in various branches of science for more than 2 or 3 centuries. Now, you see, it is well known that if one has a string constrained at 2 ends, then when one introduces, a disturbance in the string, the simplest mode of vibration is a sinusoid, right. So, it really has minima at the ends, and it acquires at least one maximum somewhere in between. That is the simplest mode of vibration. And the reason why the sinusoid or the sine wave plays such an important role in vibration or in any kind of function analysis is, it is probably the smoothest function that one can think of in a certain sense. In fact, the sine wave is related to the exponential, directly or indirectly. The exponential is also an extremely smooth function. Extremely smooth in the sense that the derivative of the exponential is again an exponential. So, any number of derivatives of the exponential exist and are continuous. So, it is one of the best known analytic functions that one deals with and is actually achieved and observed. See, it is not too difficult to construct analytic functions, but analytic functions that occur in nature are not too many. And the most commonly observed analytic function in nature is the sine wave or the exponential. The sine wave typically occurs in the context of periodic behavior. So, in the case of harmonic oscillation or in the case of any other periodic motion, the sine wave becomes an important tool of analysis. In fact, for a long time, mathematicians and scientists had been looking at the possibility of thinking of all periodic functions as comprised of sine waves. So, the idea of using sine waves as basis elements, by basis elements we mean functions or elements or objects, mathematical objects, which can be used as raw building blocks for constructing arbitrary patterns. So, the idea of using sine waves or corresponding functions derived from sine waves as basis elements has been an endeavor in physics and mathematics, as I said, for more than 2 or 3 centuries. And in fact, this endeavor we shall carry to our discussion of signals and systems. Now, some of the very important names, both in the positive and in the negative side of the development of this, building up from sine waves include, the first name, of course, very, very well known, is the name of Fourier. Towards the 19th century or so, his work has been well recognized, and in fact, today we name the whole idea of analyzing based on sine waves after him, right? I shall not go too much into the history of how Fourier developed his principles, which we are now going to build on today. Safe to say that actually when Fourier put across his ideas that one could think of periodic functions and in fact even aperiodic functions as comprised of a large number of sine waves in them with appropriately chosen amplitudes and phases, there was tremendous opposition from the scientific community. In fact, the opposition came largely from a reasonably valid issue. Namely, suppose you had a function like this. So, you have a function like this which is periodically repeated, right? So, you keep repeating this with, so suppose this period is capital T here, then we keep repeating this at every multiple of T. So, you see, the whole problem was that, sine waves are inherently analytic, inherently continuous, differentiable, and any number of times differentiable. And here we have discontinuities. So, the objection was, how can you express a function with discontinuities in terms of a linear combination of sine waves? Any finite linear combination of sine waves is bound to be analytic. So, it's going to pose problems at these discontinuities. That was one of the important objections that stalled the use of sine waves as a basis for analysis for quite a while. But people overcame that objection by realizing that except at the points of discontinuity, at all other points one could go arbitrarily close to the function in question. And at the points of discontinuity in the large, that means asymptotically, as you used more and more and more sine waves to come together and aggregate and form the function, it was only at isolated points that there was a problem. So, if you looked at the difference between the summation of an appropriately chosen set of sine waves and the original function, the difference function or the error function, as one might call it, started having zero energy, as they call it. Energy means if you looked at the squared magnitude of the function and found the area under the squared magnitude, that's always non-negative, that's always indicative of how much of error there is on a whole in the function, then this total energy in the function tended towards 0 as the number of sine waves used grew larger and larger. So, even though it was not, even though there were problems at isolated points, on the whole, there was no problem in terms of how close you could go to the function in this sense, right? So you see, so Fourier in fact put forward his work not really as a pioneer, in the sense there were people even before that who had put forward similar ideas. And as I said, Fourier was a positive development in this field. There was some other negative, in the sense people like Lagrange, very well-known mathematicians, had a strong objection to the use of sine waves, essentially because of this principle. So this tussle or this disagreement, this difference of opinion, kept the use of what we know as Fourier analysis today for quite a while. So it was, many years, maybe many decades before Fourier analysis, so the use of sine waves in constructing functions really took off in the true sense, right? Now, Fourier put forth his ideas of using sine waves as a basis. But then it was not quite clear from his work precisely in what contexts one could approximate or one could reach the function in question to an indefinite level of accuracy, and in which cases one could not. So the question was, well, is it always possible to think of functions as comprised of many sine waves, or are there instances where one cannot do so? It was found that there are instances where one cannot do so, but these instances are largely pathological. Pathological means they are instances which do not occur in most realistic walks of life. In most realistic situations in signal and system analysis, one does not need to worry about whether a Fourier representation or a representation in terms of sine waves exists or not. But one can, as far as the mathematician is concerned, as far as the pure scientist is concerned, one can construct examples of functions which do have a problem in terms of their representation in terms of sine waves. And this distinction between representability and non-representability was made by Dirichlet. So although Fourier clearly proposed the idea and made it very clear that one could use sine waves not only for periodic functions but also for aperiodic functions, it was Dirichlet who really brought out a well-defined set of conditions under which one could use the idea of sine waves as a method of reconstruction of functions. We shall be looking at the conditions given by Dirichlet in detail in the sequel. Now, before we start the discussion, why sine waves, how sine waves, and and how we construct the amplitudes and phases of sine waves that would give us the functions in question, it's first important to understand why sine waves in the context of LSI systems. See, we've been emphasizing LSI systems, and we've also explained why earlier physically, why LSI systems have an important role to play in at least the first level of signal or system analysis. So is there something about sine waves, or is there something about the corresponding functions from which sine waves are derived that make them very attractive in the context of linear shift invariant systems? We need to understand this point and then take the discussion further. You see, a sine wave can be thought of not as one but as two functions. The two functions are as follows. If we allow complex functions, and you'll wonder why complex functions, but as we proceed in our discussion, the idea will become even more clear. Let's visualize a circle of radius a0 in the complex plane. Let us visualize two complex numbers in the plane, each rotating on the circle with a velocity of omega naught, but in opposite directions. And they start from equal but opposite angles. So both of them start from an angle of theta naught. This is the starting point here, and this is the starting point here. so think of them as particles if you wish, and this particle rotates in the counterclockwise direction with a frequency, with an angular frequency of omega naught. This particle rotates in the clockwise direction with an angular frequency of minus omega naught. Now, if you think of these particles as underlying complex numbers, then their sum is always real because their imaginary parts cancel. And the sum becomes twice A naught cos omega naught t plus theta naught. Yeah. Now, let us express each of these complex numbers in their own right. That is, let us write each of them as a complex number by the use of complex exponentials. So, we may write this function as A naught e raised to the power j omega naught t plus theta naught. And in fact, we notice that this complex number shall always be the conjugate of the upper one, right. So, it would be A naught e raised to the power minus j omega naught t plus theta naught. Right. So, right at this stage, it is useful to recognize that embedded in every sine wave, by sine wave, of course, sine and cosine is not important. I mean, by sine wave, we mean a sinusoid here, right. So, embedded in each sine wave are two rotating complex numbers, rotating with the same angular velocity, but in opposite directions, right, and starting from the equal but opposite angular points on a circle, right. So, embedded in each sine wave are these two oppositely rotating, well, complex numbers, and we shall give them a name. We shall call them phasors. We shall call these two functions, complex functions, phasors. Phasors are rotating complex numbers by definition. Okay. Now, it is naturally, a very pertinent or a moot question as to why one should convert a nice real sinusoid into two complex phasors. We shall now answer the question by looking at what happens when a phasor passes through an LSI system or through a linear shift invariant system. So, let us apply a phasor. In fact, we can take the phasor in its raw form in the sense we can have an amplitude of 1 and a phase of 0, that is A naught is 1 and theta naught is 0. Because the system is linear and shift invariant, one can see that if you have A naught e raised to the power j omega naught t plus theta naught, this could be expressed as A naught e raised to the power j theta naught multiplied by e raised to the power j omega naught t. And the effect, if one knows the effect of this, the effect of this entire expression can be found by multiplying by A naught e raised to the power j theta naught as a consequence of the property of scaling or homogeneity. So, therefore, let us apply the function e raised to the power j omega naught t to the linear shift invariant system. right? Let the impulse response of the linear shift invariant system be h of t. And we query the output. Let us find out the output. We shall obtain the output by the convolution expression. So, well, the output is going to be integral h lambda e raised to the power j omega naught t minus lambda d lambda. Integrated over all lambda. This is the output. Let us simplify this. We write it as integral h lambda e raised to the power j omega naught t e raised to the power minus j omega naught lambda d lambda. And we recognize here that e raised to the power j omega naught t is independent of lambda, so it can be brought out of the integral, right? So let us bring that out of the integral. Now, let us focus our attention on this part of the expression here. This part of the expression is a constant for a given omega naught, right? In fact, it is a function only of omega naught. It is independent of time. What are we saying in this output? What is our conclusion from this output? That is right. The output is a multiple of the input. When the input is e raised to the power j omega naught t, the output is a multiple of e raised to the power j omega naught t, and the multiplying factor is the expression here. Now what are we saying in general? We are saying that there is this class of functions. The functions of the form e raised to the power j omega naught t, which when applied to the linear shift invariant system come out unchanged in form but multiplied by a constant. So they are just scaled. Now this has so many different very interesting interpretations. In fact, very soon we shall start likening the idea of signal analysis or system theory to some of the geometrical notions with which we are familiar. And then we shall be able to draw a very beautiful parallel between what we are saying here and certain geometrical notions in the context of vectors. In fact, let us do that right away. Consider an arbitrary function. Let us say it is a function of time. Visualize the function as divided into very small intervals. So we have very tiny intervals here. Similar to what we did when we thought of the function as a superposition of impulses. So let's think of it as a large number of very small pieces. And exactly similar to what we did when we thought of the function as impulses, as a superposition of impulses, visualize this interval going towards 0, in which case the function in each interval tends towards a constant. Now, here we would like to ask the question about function construction from a slightly different perspective. See, let us ask it from the perspective of vectors. Suppose I have vectors in 3-dimensional space. What do we mean by saying a vector is located in 3-dimensional space? What is, for example, the difference between a vector in 3-dimensional space and a vector in 2-dimensional space? Let me ask the class. Right? So what do you feel would be the difference between, what is it that distinguishes between vectors in spaces of different dimensions? Or equivalently, why do you say this vector is 2, or this is a 2-dimensional space, or this is a vector in 2-dimensional space, that's a vector in 3-dimensional space? What is it about those vectors that distinguishes these attributes? Yes, Nikhil, yeah.
So we'll have means the whatever dimensions refers to the number of basis vectors that we have in that vector, minimum number of basis vectors.
Very good. So the answer is, that the dimensions, or the dimensionality of the space in which the vector lies refers to the number of basis vectors. Now, what we mean by basis vectors is a set of independent elements whose linear combinations result in that vector. Another very simple way of putting it is, how many degrees of freedom do you have in constructing that vector? In a 2-dimensional space, you have 2 degrees of freedom. That is, there are 2 independent choices of coordinates that you can make. In 3-dimensional space, you have 3 degrees of freedom. In n-dimensional space, you have n degrees of freedom. Now, this degrees of freedom idea can be carried over to the realm of functions. So, if I take very small intervals here, and if I decide that in each interval my function must be almost a constant, to fix our ideas, let's assume that we are trying to construct a function on a finite interval. So, we take the interval, let's say -1 or 0 to 1, and we subdivide this interval into 100 parts. So, we have 100 subintervals, and we assume that in each subinterval the function must be almost a constant. Well, in that case, how many degrees of freedom do I have to construct the function? 100, as many as the number of subintervals. So, somewhere this interval, or the number of subintervals, relates to the number of degrees of freedom that I have in constructing the function. Another way of thinking of it is, I could think of small functions which are in the subinterval and 0 elsewhere, small pulses, exactly as we did in the context of construction of, the convolution integral. So, we looked at pulses initially, and then we scale these pulses by the value of the function, and therefore you could think of the function as a linear combination of a large number of pulses located in the appropriate subintervals. So, just as you have basis vectors in 2-dimensional space, you have basis functions whose linear combinations can give you the function in question. One can start seeing the parallel between functions and vectors. Of course, we are moving slowly from a space which has a finite number of dimensions, like 2 or 3-dimensional space, to a space which tends towards an infinite number of dimensions. So, in the large, as you start allowing more and more freedom, and as you start making the interval smaller and smaller, the number of degrees of freedom tends to infinity. In fact, for an arbitrary function, there are as many degrees of freedom as the points on the time axis, if it's a time function, or there are as many degrees of freedom as the number of points in space, if it's a spatial function, and so on, right? Correspondingly for discrete sequences. So suppose we have a sequence, a discrete sequence. Again, let's fix our ideas by constructing a sequence which is non-zero only over a compactly supported part of the integer axis. For example, let's take a sequence which is non-zero between, say, 0 and 4. So the sequence is 0 elsewhere. Here and here. Now, as I said, you see, certain things become so much clearer or are so much easier to state in the context of discrete time systems or discrete time signals. So here again, it's very clear how many degrees of freedom there are in constructing a sequence which is non-zero between 0 and 4. There are exactly 5 degrees of freedom, because at each of these points one can choose the samples independently. The other way of stating it is, I could think of 5 different sequences. The sequence delta n, the sequence delta n minus 1, and so on, up to the sequence delta n minus 4. And the set of sequences that you can get which are non-zero between 0 and 4 are linear combinations of these. So one way is to think of one way to understand the situation is to think of these sequences as a set of basis vectors. In fact, we can go a step further. We can ask, is there some notion of perpendicularity? For example, in 2 dimensions, one could have 2 perpendicular vectors from which you can construct any 2-dimensional vector. That's what we normally do when we express a vector in 2 dimensions. A similar question can be asked in the context of sequences. Well, in fact, one can bring in the notion of perpendicularity in sequences also. We shall do it as we go along, but we'll do it after a while, right? Even so, at this point, it's very clear that there are 5 degrees of freedom. In fact, there are as many degrees of freedom as the number of non-zero points that you allow. And now if we carry this argument to arbitrary sequences, then we have as many number of degrees of freedom as the points on the integer set. So for every integer, we have 1 degree of freedom in constructing a sequence. So that gives us a space which has an infinite number of dimensions. And that, infinity again has various degrees. There are various levels of infinity, and when we are talking about sequences, the number of degrees of, the degree of infinity is the same as the degree of infinity of the set of integers. That's because the coordinates, you could think of this sequence as a vector with coordinates. What coordinates? The coordinates which occur as coefficients in the linear combination of these unit impulse sequences. And those coordinates specify the sequence completely. There are as many independent coordinates as the number of points on the integer set. So that there are that many dimensions. So we are talking about vectors in a space which has so many dimensions. In the case of sequences, as many dimensions as the number of points on the integer set. In the case of continuous time or continuous space functions, in the large we are talking about as many dimensions, the number of points on the real axis, whether if it's 1 dimension or on the real plane if it's in 2 dimensions and so on, right? Anyway, the point is that there is a 1-to-1 correspondence between signals and vectors. And this correspondence is extremely important in being able to interpret certain properties of both signals and systems. We come back to our conclusion about the effect of a linear shift invariant system on an exponential, a complex exponential, from this perspective. So, we said in our earlier discussion, we concluded that when e raised to the power j omega naught t passes through a linear shift invariant system, with impulse response ht, the output is, now I shall write it in a slightly different way. I write the output as h of omega naught times e raised to the power j omega naught t, where h of omega naught is integral h lambda e raised to the power minus j omega naught lambda d lambda. We had earlier emphasized that this is a function purely of omega naught, right? Now we would like to view this property or this conclusion from our perspective of vectors. What are we saying in the language of vectors? You see, this is a constant for a given omega naught. So we are saying there is a vector that goes into the system and comes out as a vector multiplied by a constant, which means the output vector is collinear to the input vector. It lies in the same line. When you multiply a vector by a constant, it results in a vector that is collinear. Now, you see, that raises the question, how can I interpret the operation of a system in the language of vectors? So let's take, let's again go back to the situation of two dimensions. Suppose I have a two-dimensional vector and I have a system that rotates the two-dimensional vector by an angle of 45 degrees. I'm sure all of us will recall from our elementary matrix theory that if if you think of the vector as a pair of coordinates, right? Let's say the coordinates are x1 and x2. Then a rotation by an angle of theta naught or theta 1 can be written down as a matrix operating on the vector, and the matrix is given by cos theta 1, sin theta 1, minus sin theta 1 and cos theta 1. So it's a 2 cross 2 matrix. This causes a rotation of the two-dimensional vector by an angle of theta 1. Right? In fact, the same concept can be extended to systems. So you see, in the large, the operation of the system is like a generalized matrix operating on the coordinates of the vector corresponding to the signal. And therefore, see, of course, remember, this kind of a matrix representation is not possible for all operations. To take an example, if one shifts a vector, right, the operation cannot be represented by a matrix. It requires another vector. Right? So you see, that again brings us to the difference. I mean, all systems may not have this kind of the equivalent of a matrix representation. In fact, the equivalent of the matrix representation is what we've been calling convolution all this while. In fact, let me write it down in that form to emphasize the point. Right? You see, it will be easier for us to write this down in the context of discrete time systems. So let's take the discrete time system with input xn. The system is linear shift invariant. and has an impulse response of Hn. So the output is Yn described by summation on k xk h of n minus k. Now let us write this relationship down in vector matrix form. So let us visualize, see, in fact for the moment let us visualize a vector corresponding to the sequence x, right? And let us look at, x, say x minus 1, x 0, let us take only a few of them, right? x1, x2 and so on. Let us look at only a few of the entries. This is actually, it's an infinite length vector if you look at it. It's an infinite length vector, right? And let us, for example, take the output at the point 0, y of 0. How would I get y of 0? I will get it by you see, how do we get y of 0? X of 0 is multiplied by h of 0. So, you see, you can visualize it as multiplying this column vector by another row vector here. That row vector has an entry of h0 corresponding to the entry x0 here. Similarly, x of 1 gets combined with h of minus 1. So, corresponding to the entry h of x of 1, you have the entry h of minus 1 here. Yes? And then of course, corresponding to the entry h of x of 2, you have the entry h of minus 2. And here we have the entry h of 1 corresponding to x of minus 1. I mean, this corresponds to this. And then all the others correspond accordingly. Yeah? So one can extend this vector, this row vector also infinitely in both directions. Is this idea clear? Yes? So you could think of it as a row vector multiplying this column vector to give you a number at the point n equal to 0. Right? Now what happens at the point n equal to 1? Well, you see, x of 0 gets combined with h of 1. So you see, the whole thing is, this thing shifts forward here. So h of 1 now comes forward, h of 0, all of them go correspondingly forward. So it's very clear that the row vector that you need to construct y of 1 is this row vector shifted forward by one step. So now we have, in fact, now you can visualize a matrix where the row vectors are stacked one on top of the other. Right? One can visualize a matrix where the row vectors are stacked one on top of the other. As you go down in the rows shift one step to the right. As you go up the rows shift one step to the left at every, instant. And therefore, you could think of the operation of the discrete time system as a matrix operating on this column vector to give you another column vector which corresponds to the output. So, what have we concluded from this example? That just as you can think of, signals or sequences as vectors, you could think of systems as matrices operating on the vectors, right? And of course, it's a little more difficult to see what implication this has in continuous time or continuous space, but a generalization can be made. If you're willing to arrange all the points in time, though of course I agree they are infinite in number and uncountably infinite in number, but still one can visualize an infinite length kind of arrangement of the points here, then you have this very dense object. Here you might think of this, see, a matrix can be thought of as, a two-dimensional object where discrete points have been given numbers. Now for the continuous time case, you would have to think of it as the continuous two-dimensional space having been given numbers everywhere. So that's how you would have to think of it that way. So it's a continuous version of a matrix, if I might call it that. Just as you have a continuous version of a sequence which gives you a signal, you might have a continuous version of a matrix that gives you a corresponding operator for the linear shift invariant system in continuous time, right? In fact, we give that kind of a continuous matrix a name. We call it a kernel. It's called a kernel of the corresponding linear shift invariant system, right? Doesn't matter. The names are not important, but the idea is, right? But the idea is that there is something like a matrix operating on the vectors. Now, what have we said then in the language of matrices? This vector is operated upon by the matrix to give you another vector which is a multiple of the original vector. This rings a bell in our understanding of matrices. Recall that matrices have eigenvalues and eigenvectors. What are eigenvectors in a matrix? Eigenvectors are some very special vectors of a matrix corresponding to a given matrix. They are peculiar to the matrix. Of course, to square matrices, they are peculiar to square matrices. So, given square matrix has a set of eigenvectors. And what is the beauty of these eigenvectors? When they are operated upon by the matrix, the result is a vector which is collinear to the original one. That means which is a multiple of the original one, right? And the multiplication factor is called the eigenvalue, right? We shall continue from this point onwards in the next lecture to take this eigenvalue-eigenvector relationship further in our discussion. Now that the attendance is very poor today, right? What is the reason?